This is an exciting event. It's wonderful to see so many folks who have been involved or just interested in this area for so many years. And it's wonderful to talk with you this evening about many different things, all related. So I am going to moderate this discussion, and the way this is going to work is that we'll have a couple of presentations. I'll just introduce the topic a bit, and then we'll have a couple of presentations, and then we will have some discussion of these things by the entire panel. So let me just mention who's here in case you're having trouble reading the 12-point font there. So next to me is Carl Dietrich from Terrafugia, and I think you'll find a lot of his previous work where he's flown real airplanes and designing some interesting new concepts, very interesting. Nikhil Goel is from Uber, and I'm sure many of you have seen their very interesting discussion of what the future of on-demand aviation may be. So I'll look forward to that. Zach Levering is from Airbus Silicon Valley, also known as A Cubed. And Zach will tell us a little bit about some of the things that they are doing, which I find very exciting too. Aleksey Matushev is doing something a little different from some of the other folks here, but is involved still with a combination of autonomy and interesting propulsion and very different kinds of operating concepts. And finally, Jeff Schox is from Trucks Venture Capital, because we can't do all of this without people who are interested in supporting it. So that is the panel, and so after the presentations, we'll have some questions, and then the audience can text some questions that we will then address subsequently. And up in the right-hand corner there, it says text your questions to 650-308-8522. So I'm looking forward to an interesting discussion. And the goal here is to ask difficult questions, ask technical questions, social questions, the broad range of topics that relate so much to thinking about the future of transportation. I can't give a talk without showing pictures of airplanes. So I am the moderator because I can't really say too much about what the folks working with me have been doing for the last 8 or 9 years. But we have been thinking a lot about this for a long time, and we'll try to ask questions that may be of interest to everyone. So I'm going to just start out with a broad introduction to this idea, and then we will go straight to Carl's presentation. When most people think about autonomous vehicles these days, they think of self-driving cars. This is a picture of a self-driving car developed at Stanford, entered into DARPA competitions for driving in the desert, driving in urban environments, etc. It's a very difficult problem, but one that people have made great progress on, as most of you well know. What many people in the general public don't know is that it's actually somewhat easier to fly autonomous airplanes or driverless airplanes. And these have been around for quite a while. So this is Global Hawk, developed in the 1990-ish time frame. It is an airplane that flies at high altitudes with a jet engine, taking pictures of things from those kind of conditions. This airplane is not so much about what we're going to talk about, but was one of the precursors to a set of autonomous airplanes that we think now could do many more things than people imagined when drones first came into existence. So we call them drones because UAS is such a horrible acronym. But they started out being flying airplanes that were used for target practice for fighter pilots and really had no artificial or otherwise intelligence and were shot down. These days, autonomy is a very important part of everything we're going to be talking about tonight. These kinds of things then have been used for other kinds of drones. So putting together autonomy with electric propulsion in this case and solar propulsion allows one to stay in the air. In this case, AeroVironment's Helios airplanes and the Pathfinders that preceded it flew on solar cells up to 100,000 feet. And the idea was to recharge batteries or fuel cells overnight, stay in the air forever, or at least a very long time, and do things that what people had thought about drones doing had never done before. So this is kind of a first inkling as to what this might be. If you see the date there, that's 2001, when that picture was taken near Hawaii. As the technology improved, we started being able to build smaller things. And this is a DJI drone that does automatic obstacle avoidance. It has very high definition cameras, gyro-stabilized cameras, and can do all kinds of things, including things that people would rather it not do, maybe in their backyard, for example. So when we start thinking about vehicles that have their own autonomy, that can do many things from delivering images to delivering pizzas, and then things that might deliver people, we should think about the implications more than technical, because we're getting quite far technically. Nearby here, here are some of Stanford's new rules that are posted. In the upper part, you see someone walking a dog. Dogs must be leashed. And in the bottom part, you see a quad rotor with a line through it. And I hope that's not a predator, but all kinds of flying things. No flying objects zone. So these signs are posted all over campus, and there is now a policy on how to fly things on campus. So perhaps we have figured out how to make some of these autonomous airplanes quite small. We probably can make them even smaller. Here's some very tiny quad rotors and rotors in general. But we're going to be talking a lot tonight about applications that are not close to smart dust, but rather related to transportation. So when we think about the connection of autonomous vehicles, vehicles that can fly differently from conventional transport airplanes, we have to stop and think a little bit more about transportation in general. And this is a plot of, on the vertical axis, the number of miles in the US that passengers travel per capita per day. So this is a log scale and starts out with 0.1 on the bottom there and goes up to about 100. And what you see is that we don't travel very far on average by train, that peak horse occurred a very long time ago. And that aircraft have been increasingly useful in providing the transport of average people in the US and in fact around the world. So, as we know, air transport has been actually a very efficient way to travel long distances. And in particular, we can increase the efficiency of these airplanes even more. But to travel thousands of miles, we want to travel at higher speeds. And so airplanes like this might be a way of compromising between the Mach 0.8 something airplanes that we fly in these days and airplanes of the future that would fly using, in this case, 70% less fuel and a combination of hybrid electric propulsion and fuel cells. While this is likely to remain an important thing in the world, we're seeing an increase in the percentage of people who live in urban environments. It was only a few years ago that the number of people in the world was equally divided between urban and rural environments. And very quickly, if we look out to 2050, for example, we're going to see a much larger fraction of people living in urban environments, the rise of megacities, and those megacities are going to be closer together than the megacities of today. And so there may actually be a need for a different kind of transportation than just taking your car somewhere locally or traveling thousands of miles somewhere. And this is where some of the on-demand aviation ideas are important, and also where the technologies that we're seeing of autonomy and electric propulsion and improved batteries and improved sensing and even lower cost flight enabled through new manufacturing techniques may be very, very important. So if we look at what might be possible in the future, this is a NASA concept by Mark Moore at Langley, where in this case a very minimal airplane takes off vertically, allows you to fly some distance on electric power, and allows you to land. That does look like a long ways from reality, but it's amazing what people will do. So this is actually the first prototype of the Evola VC1. And it is many rotors that lift a pilot up, and it hovers. Here is a more recent version of that taken earlier this year, and has a fuselage and some protection. And it's an interesting concept, and how it is that you design airplanes like this as opposed to airplanes that look like 707s. It's a very interesting technical question, but it also is a very interesting societal, regulatory, economic question. Working on some of these things, we'll hear in just a bit from Nikhil at Uber, who has thought a lot about this, and we will ask questions to Zach Levering about airplanes that might evolve from that. This is a combination of fixed lifting surfaces and rotors, which allow a lot of flexibility in takeoff and landing, but yet high efficiency in flight. So that's how it looks when it's cruising along in one incarnation, and this is another view of it in the vertical takeoff mode. So it's very exciting to think about what might be possible. And before I introduce Carl Dietrich, I would like to suggest a few things you can be thinking about as people talk. And these are, is this real pie in the sky things? Is this something that we're going to see suddenly appear that we can go buy? Or are these things that may never even happen. What are some of the, and this is a very long question, but you could be thinking about many aspects of this. What are the barriers to making this happen? Technical, regulatory, environmental, social. There are many questions that really have to be addressed before this becomes part of our everyday life. What kind of infrastructure is needed? If you could go out and buy one of these things now, you could not take off from your backyard probably, and if you could, you probably shouldn't. But thinking about the infrastructure is something that's very important. How these things interact with ground vehicles might be very interesting. And we can ask how it is that some of this technology can be scaled up. Are we going to have things that look like Airbus's Vahana aircraft that carry 100 people? Should we have that? There's some very interesting scaling laws in the physics that say that that will be harder than it sounds, and some other interesting social questions about that. If we did have these and the infrastructure and everything else, how would that change society? And is that something that we want? And finally, what should we do now to make this happen? Or what should we do now to make this not happen, depending on your point of view? So there are many interesting things that we need to think about in these early days of building ideas that will change our lives in the future. And I think there's no one better to start out this discussion than Carl Dietrich, who has built airplanes that actually do carry people and some real flying cars. So, Carl.
Well, thank you very much. It's a privilege to be here talking to a group of folks who are all very interested in the idea of a practical flying car. Terrafugia really is about enabling a new dimension of freedom and personal mobility. And as Ilan said, my name is Carl Dietrich. I'm the CEO and co-founder of Terrafugia. So I want to start with a little bit about kind of why now. Why are we all here today? Certainly, I think things like the presence of some of the big companies that are starting to invest in this space, that's one part of it. The interest that Uber and others have shown in catalyzing the creation of a new industry. But for me, our company is here because we have a couple of, I think, very interesting opportunities. One is that we've all seen that autonomous flight software is fairly pervasive. It does have the potential to increase the level of safety and potentially decrease the training time required for personal flight. It also has the potential to be more fundamentally empowering to the individual than autonomous driving. I would venture a guess that most of you in the audience can drive today. How many pilots do we have in the audience? Okay, not bad, pretty good, But that, in the United States, we have about 600,000 private pilots, and that number is not increasing today. Terrafugia was formed back in 2006. We spun out of MIT in partial response to a regulatory change. The FAA created a new category of aircraft called light sport aircraft that takes half the time and half the money to learn how to fly one of these little simple to use airplanes. They also created a new way of bringing a product to market that required less capital. It sort of recognized that, hey, the low end of general aviation is fairly stagnant due to the primarily small size of the market that exists today. When they created this category, we said, well, this is really interesting. The FAA doesn't loosen things up very often. What could we do? How could we best leverage this sort of change and potentially have a big impact on the general aviation industry? And we looked at the problems that pilots encounter on a daily basis. And those problems were fairly well quantified by a former professor of mine at MIT, John Hansman, who conducted a survey of the pilot population, statistically identifying the largest obstacles to the more widespread use of general aviation. Weather sensitivity is the biggest problem. That's what pilots list as their top reason why they don't choose to travel by aircraft on most of their trips. The second big problem is the high recurring cost of ownership. The third biggest problem is the long door-to-door travel time, because what matters is how long it takes me to get where I want to be, not just how fast I'm flying in the air, even though that's what most aircraft manufacturers advertise. And then finally, the United States has a network of about 5,200 airports. On average, there's one airport within a half-hour drive of wherever you are. It's our nation's largest underutilized transportation resource. Most of those airports have no ground transportation infrastructure. There's no taxi cab stand. There's no rental car counter. So pilots identified that lack of ground mobility as a major obstacle. So we said, well, these are the big problems in this industry. It's a well-known industry, well quantified. Let's see if we can leverage this rule change to bring a product to market that has the potential to disrupt this by addressing those questions. And we worked on this combined flying driving vehicle platform that makes personal aviation less weather sensitive, because you can always count on it to get where you want to go no matter what happens with the weather. If the weather comes in, you can drive home. It reduces the recurring cost of ownership because you can keep your aircraft at home in your garage. It runs on normal automotive gasoline, which is significantly less expensive than aviation fuel, and it gets comparable gas mileage to most cars on the road while flying overhead at 100 miles per hour. We also, so we've been working on that for about 10 years. Earlier this year, we finally received the final special consideration that we needed to bring this sort of unique product to market from the FAA. We needed a special weight and stall speed allowance. The other nice thing about this category of aircraft is that this type of aircraft is not formally FAA certified. The manufacturers declare compliance to a set of industry standards. That's a big deal because for any of you guys who are looking at certifying software, particularly autonomy software, safety critical software is a huge expense. It's about $1,000 per line of code to certify safety critical software. That could be a big barrier to bringing some of this new technology to market. By bringing a product to market in this light sport aircraft category, we bypass the entire certification process for software. So that's a huge advantage that we're looking to take advantage of now and bring a product to market that can convert between flying and driving modes in 40 seconds, flies up to 400 miles at 100 miles per hour, has a 20-hour training minimum, and with the autonomy, we may actually be able to achieve something very close to that minimum 20 hours of training required, providing things like autonomous takeoff and landing, GPS waypoint navigation, ADS-B-based collision avoidance, airspace geofencing, engine monitoring, trend identification, full envelope protection, and autonomous ground collision avoidance. A lot of these technologies are reasonably mature, and we're not actually developing a lot of them. We're actually incorporating them onto our platform. With a direct operating cost to end users of about $25 per hour and a shared use pricing potential in the $70 to $100 an hour range, we think that there is quite an exciting market for this, particularly if we lower that barrier to entry and continue to push it down, make trips from here up to Napa for lunch a practical thing. This is that existing airport infrastructure in those circles there. We've got one circle centered around San Francisco, another centered around Boston, where our company is based. Shows you what's within range of one of these vehicles. So you could go from the Bay Area here down to Los Angeles. You could go from LA to Vegas in a couple hours, Tahoe to San Jose, Boston to New York, Palo Alto to Napa. So you bring a lot more utility to personal travel, and you don't have to worry about the traffic. It's a huge, huge advantage. I already mentioned some of these regulatory enablers. In addition, we are seeing the steady progress of the integration of unmanned aircraft into the commercial airspace, the UTM movement, which is very exciting and could really open up, particularly for a next generation type product that is the urban vertical takeoff and landing market, could really help open those markets where people want to take off and land within a few miles of a major airport. And we're starting to see a lot of interest from China. The low altitude airspace is starting to open up in China. So that's very exciting because today Chinese general aviation is basically nowhere. They have about 2,000 airplanes in China. We have 200,000 airplanes here in the United States. All that is going to change in the coming decades. So we're destined to see some very significant growth, particularly in that type of emerging market. Our company, one of the unique things, because we got a head start on this space, we just received all of the final regulatory considerations that we need, special considerations, in order to ship a product. 2 exemptions from the FAA, 4 exemptions from the National Highway Traffic Safety Administration, rule clarifications from the EPA, the California Air Resources Board, basically all the things that you need to actually bring a combined flying driving vehicle to market. In terms of special consideration, we've got it. We're now heavily involved in a number of the aviation committees, including the ASTM committees that are writing the standards for not only certification of all future general aviation aircraft, but electric propulsion, that sort of thing. And leadership positions also inside the General Aviation Manufacturers Association, which is one of the most powerful lobbying organizations in our industry. A little bit about our team. I think this is one of the reasons that we really have been successful and why we have managed to survive for a decade in a pre-revenue state. It's a challenge to bring this type of technology to market with the incubation periods that it inherently has. We've got folks from both aircraft, aviation backgrounds, myself, Dave Stevens, our program and certification manager, was with Quest Aircraft. He's a Caltech guy, but we hired him anyway. Strong background from big aerospace as well. Some folks from the automotive industry, guys who have done electric and hybrid electric vehicles, solar cars, very lightweight vehicles that have to be robust enough to actually survive long drives across the Australian outback, that sort of thing. And we've got a very mature flight test program that we've been flying vehicles since 2009. We've also partnered with a number of major organizations, partnering with the FAA and NASA to try to help to figure out how autonomous software can be certified. Strong relationships with MIT, recently added some folks from Lockheed Martin Skunk Works to our board of advisors, and a number of great industry partners. Our long-term strategy, basically, we can't afford to be as risk-taking as some of the other companies that you'll see here because we're small. We're focused on getting a product to market very soon. We're talking about getting our first product to market that has the potential to truly be an autonomous flying car to market within the next 3 years. It is a longer range vehicle. It is using the airport infrastructure that is already in place today. So we're not doing the vertical takeoff and landing within the next 3 years. That requires some significant change, which we believe is going to happen. And we believe a lot of the companies that are represented here are going to help enable that type of change, both to regulation and to the politics of putting in vertical takeoff and landing heliports, vertiports, where they need to be, where people want them, where they would be most useful. We would like to see over the next decade that type of market develop, and I think it has the potential to with some of the resources that are being harnessed now, and we certainly intend to be a participant in that space. In the long run, we do believe that there is even bigger potential out there, and we've published a concept that is a vision for the future that relies on some technologies also that don't exist today. Of course, our first product, all the technologies are there. The second generation, most of the technology is basically there right now to do this type of urban vertical takeoff and landing mission. The challenges are not as much on the technology side, more on the actually getting it out there, getting it certified, getting it, there's a lot of work that has to go into that, and dealing with the local cities, dealing with putting in these vertiports and all the politics associated with that. So, but we believe that in the long run, this has tremendous, tremendous potential to disrupt the way people get around. So with that, I will wrap it up, and with just the conclusion that the future of personal transportation truly is airborne autonomy. And at Terrafugia, we're very excited to be in on the ground floor. Thank you.
Thanks everyone for coming. So who here drove to get here today? Okay, oof, lots of you guys. Who took Caltrain? Anyone taking Uber? This is the wrong city to ask that question. So hopefully most of you are familiar with Uber and our mission. Uber did not start with any grand ambitions. It started with a super simple premise: push a button, get a ride. Today I want to talk to you, to everyone here, a little bit about push a button, get a flight. Get a flight. So this here is an artist rendering that anybody who read our white paper would have seen. This here depicts a vertiport, which is basically a form of a heliport or a helipad, but within an urban core. And so this particular instance of a vertiport is a converted parking garage at the top of a parking garage that you may see in the middle of a city. It would have about 10 parking spots. It would have charging stations for vehicles, and it would have 2 takeoff and landing pads. It's one of the depictions in our paper. And in our paper, we talk a lot about the different forms that a vertiport may take. But this all started with us thinking about the commute between San Francisco and San Jose. So who here lives in San Jose? San Francisco? So I live at the very top of the San Francisco in a district called the Marina. And this all started with us thinking about, well, what if you could get from the Marina to San Jose? That's a drive that takes normally about 2 hours during rush hour. What if you could get there in about 15 minutes? And not only could you get there in 15 minutes, but what if you could get there for only $20? And what if this was very non-variable? What if this was something that you could do as part of your daily commute, and it was something consistent that you could expect because it was through the air? And so there were no roads to worry about, no traffic, no construction, no changing conditions, but because of the 3D nature of air travel, it was something you could consistently rely upon. And so that's where the vision for our Elevate initiative started. And so we wrote a white paper. Who here read the white paper? And so the media has a lot of different, it seems like they got the page counts wrong, but this one here is 97 pages, 99 pages. I think this one's 86, 98. Point being, it was a very large white paper. It was a very large effort by a small team at Uber and a number of consultants at NASA and across the industry. But it's an area where we put a lot of work into not only articulating this vision, but more importantly, articulating what's out there today and all of the blockers that kind of exist in the industry today. And so, this all started out with thinking about, well, what does my team do at Uber? So I work closely with Jeff Holden, our Chief Product Officer, and our team's core mission is to advance Uber's mission. So Uber's mission is, of course, as people probably recognize, to provide transportation as reliable as running water to everyone, everywhere. And so thinking about that is a large part of what I do every day of how do you take that mission and how do you advance it even further? How do you advance our products and our core offerings to the next level? And then the second thing we think about a lot is disruption. So thinking about disruption threats, thinking about what other companies are doing, what other technologies are bringing to the marketplace, and how could our core model be disrupted? And the last is paradigm shifts, thinking through what forms of technology such as augmented reality, virtual reality, autonomy, both on the ground and in the air, how does that affect our core business and how does that affect Uber's kind of future? And so all of this builds up to thinking about our team is almost the immune system of Uber. Think of it as the immune system against, call it just the immune system of Uber, thinking about plagues or thinking about how the current system may become stale. And a lot of the things we think about are big, bold bets. And so if you're not thinking 5 to 10 years in the future, then there's no company in 5 to 10 years, right? And so how does Elevate fit into all of this? Well, first of all, advancing our mission. Even though it's not explicitly stated in our mission, a lot of what Uber's value proposition is giving time back. And so giving time back to our riders, giving time back to our drivers and to the community. And obviously, if you can fly, then you can get from point A to point B a lot faster if you're going 200 miles an hour. The second is commute. So today, Uber does not do a great job serving long commutes. The San Francisco to San Jose example I was talking about, it takes 2 hours in rush hour. And it's quite expensive, even if you've got the time. It's just not a reasonable thing to do every day in an UberX or even an Uber pool. And so if you could, again, do that commute in 15 minutes, then it serves the commute use case a lot better. And then timing. As we looked at the various technology for urban aviation, technology is getting to the point where there are dozens of players thinking about different vehicles, where there are cities thinking about how do we implement this solution in our markets. And so then the natural question was, well, why don't we fly helicopters everywhere? So we've got an Uber Chopper product that some of you may have heard about. We fly this between Dubai and Abu Dhabi. We're flying some in Sao Paulo. We're flying some in several markets around the world. Well, why don't we do this? And on top of that, there are landing sites for helicopters. California itself has 880 public and private airports. This is myself and Jeff and David Pluff, one of our senior policy advisors, up actually on the top of Uber headquarters. There's actually a helipad up there. But there are 28 emergency landing sites in San Francisco alone where a helicopter could technically land. Turns out people don't love noise. So this photo is from the Santa Cruz Mountains, where over 3 million complaints have been lodged against a flight path into SFO because of noise. I don't even think 3 million people live in Santa Cruz. I don't know where the complaints are coming from, but over 3 million have been lodged. And it's not just noise, right? It's efficiency, it's emissions, it's safety. So here on the left is a helicopter, obviously, which has one large blade. And because of the fact that it's got one large blade, the faster that helicopter goes, the faster the tip speed is. And then as the helicopter goes faster, it approaches the speed of sound, which if it were to exceed would cause a sonic boom. And so not only are they loud, safety is also a concern. Flying is considerably less safe than driving, at least in a helicopter. Emissions is a concern, right? Electric power has 0 operational emissions, and then as you get more efficient, then operational costs also go down. And so what's the solution to all this? The solution is something we talk a lot about in our white paper, which is distributed electric propulsion. And the best analogy I use for folks is taking all of the mechanical complexity that a helicopter brings and converting that complexity into a software problem. And I'll talk about that in a second. So DEP, basically, the concept is taking that one big rotor and turning it into a lot of tiny rotors. And if you do this, it's very quiet compared to a traditional combustion engine approach. And because you have a lot of smaller rotors, then your tip speed goes down, and as a result, your noise also goes down. It's also inherently safer because you have several of them, numerous of them. If you lose 2 or 3 or even 4, it's okay. Redundancy is built into the system, and your aircraft will continue flying. And our goal in the paper, largely enabled by DEP, is that we want to be twice as safe as driving. Another thing we talk about in our paper is tilt rotors. So what's pictured here, basically the rotor would be in vertical position going upwards during takeoff and landing, and then it would slowly transition to a horizontal position for forward flight. And so I'm going to show you a video of the Joby S2. This is Joby's a company here in the Bay Area. I think they're located down in Santa Cruz. This is their S2 concept. And so you see the tilt rotors that I was talking about. They tilt up for takeoff, and they'll do the same for landing. And then as it gets higher, you'll see that they'll tilt forward into forward flight. And so this, there's a couple of things I don't want the crowd to take away from this video. One is I think this shows 1 or 2 people, and it shows only one guy in there. You would not be piloting the aircraft yourself, unless this could be an autonomous aircraft. The second is you don't necessarily have to have a palatial estate to fly in one of these, right? I think this is showing some guy in his beachfront property. We talk a lot about our paper about mass production and bringing the cost of a VTOL aircraft and flying in a VTOL aircraft down so that this can truly be for the masses and ultimately cheaper than car ownership. And so the good news is that over a dozen companies are developing VTOL aircraft today. And I think we'll talk about some of them. Obviously, Terrafugia, we've got Aero and Zach here. We've talked about the Volocopter, Airbus, Aero. And so there's a number of companies that aren't even on this slide that are developing aircraft. And the inbound from our paper has been enormous. We've probably talked to several dozen companies that are developing everything along the range of vertical takeoff and landing aircraft. And so it's not just the vehicles, though. It's also infrastructure. And so for those of you who read our paper, we actually did a study in Los Angeles and London. We took a small proxy of long-distance Uber trips. And we said, okay, if the demand for VTOL trips were to look the same as those long-distance Uber trips, where would the ideal locations for vertistops be? And what we found was that they actually served a lot of the underserved routes that either aren't served by infrastructure today or aren't served by existing mass transit lines today. And what we found was in Los Angeles, you could actually cover 60%, almost 2/3 of long-distance trips with only 25 vertistops, which was incredible. And if you think about other systems that exist or that are being proposed, London's high-speed 2 rail, for example, is I think on the order of 28 billion pounds. And if you were to take just some of that and build vertistops instead, you could build these amazing luxe vertistops at only a fraction of the cost. And obviously over time, you can begin to serve even more and more and more trips. And then finally, looking at, we built an intricate model thinking about what are the fully loaded costs of not only the aircraft, but also the fully loaded end-to-end system with the infrastructure, with the real estate rental, with the operational costs, pretty much everything involved. And what's interesting is that we actually project this will be comparable to car ownership, cheaper than car ownership. And so obviously car ownership will continue to go down, but as VTOL technology matures, as it becomes autonomous, as it becomes forward-placed, as it becomes faster, we believe we can get to about 33 cents price per ground mile equivalent that you would take in a car instead. And so why did we write a white paper? Why didn't we go build aircraft, or why did we choose to play the role we did? Well, largely it's what I talked about earlier. There's a thriving ecosystem of aircraft developers today. There's over a dozen folks, and rather than build an aircraft ourselves, we'd rather fast forward the entire ecosystem. And then second is we want to be a catalyst in this. So one of the largest barriers that a lot of the vehicle manufacturers we speak to talk about are standards. And so thinking about, well, how can we convene a group of stakeholders to build consensus-driven standards when we go talk to the FAA or EASA? Thinking about infrastructure, thinking about the relationships we have with cities all over the world, and how can we go talk to the cities and figure out what their barriers to building infrastructure are? And then how can we build all of our learnings from ride sharing and bring those to VTOL? So you can imagine taking an Uber poll, but in a VTOL, so the cost actually goes down because the vehicles are always flying at 100% utilization. And then, so for our next step, as I mentioned, we're talking with a host of vehicle manufacturers, we're talking with cities, we're talking with regulators, and we're going to continue that for the next several months. And then early next year, we plan to convene a summit where we can bring all of these folks together and have a really engaging discussion about what we've learned and further elaborate on the role that Uber is hoping to play. So that's about it. If you've got questions or feedback, definitely email them to elevateduber.com, and I hope everyone reads the white paper.
Great.
Great, thanks.
Thank you, Nikhil.
Hi, I'm Zach Levering. I work at iCube. That's the Silicon Valley outpost of Airbus Group. My project is Vahana. You saw a picture of it up there earlier. It's a vertical takeoff, autonomous, or self-piloted as we call it, electric aircraft. We are intending to fly it next year, end of next year, as our first prototype. And then within 2 years after that, we're having our full-scale demonstrator to demonstrate the entire capability of the aircraft, including manned flight. So the things that I am very interested in are, so I came from Z. I worked at Ilan for 4 years, and it was an extraordinary place to work. And these type of vehicles have always been very close to my heart. The interest in these vehicles, in the vehicles that Joby's building, that Z's building, that we're building, are something that I find are going to be revolutionary in terms of changing transportation. So it's been an honor for me to be part of it. So I look forward to hearing your questions.
So hello everyone, my name is Aleksey. We come from Natilus. We're probably the only company in this panel that actually are not building flying cars. And we actually come from general aviation industry as well as military, and we shy away from electric cars because we don't believe this is the time. So we're probably more of the pessimistic perspective that you'll hear today. And I have a bunch of questions myself for the panelists, is what they're working on. But at Natilus, what we're doing is actually building large-scale drones, the size of a Boeing 747. And we're targeting that for international air freight. So we believe that the future of autonomy, specifically large-scale drone, is international air freight. And so we don't fly over occupied space, which is one of the ways we are able to get away from regulation. And yeah, we're building a 2,200-pound Predator-sized drone, which will have first flight in March. So we're really excited about that.
My name is Jeffrey Schox. I wear a couple different hats. I am a patent attorney and a small boutique up in San Francisco. We do some of the work for some of the best startups here in the Bay Area. We wrote all the patent applications and developed the patent strategy for Cruise before it was acquired by General Motors. I also wear a hat of an angel investor. I've made over 60 investments, including I was the first investor in Twilio that had a nice IPO earlier this summer. And last January, I am one of 3 partners in a new venture fund called Trucks Venture Capital. And we've probably made, we made 2 and we've committed to a 3rd, which means we've probably made more autonomous vehicle investments than anyone else. We've made 10 investments so far. Our fund is focused on autonomous, connected, electric, and shared, effectively the future of transportation. A small portion of that, probably about 10%, will be in the air and on the sea, but most of it is on the ground. The one that we're looking at today is in the air.
Okay, thank you very much. Okay, we have a few questions from the audience, and it's just 8 o'clock, so we are on time. I'm going to suggest that don't stop asking questions. So as we continue here, text questions to the number in that upper right corner, and we will continue that discussion. Let me again encourage you to ask difficult questions. And I thought actually maybe we could start out with Aleksey, since he's the pessimist, as he said. But no, I think that some of these questions are really important, and I'd like to give him the opportunity to ask something of the rest of the panel.
Sure. So is this on? Okay, good. So when we looked at the space, and we've been looking at the space in general aviation almost every single year. So every single time I started in general aviation, about 2010, every single year we designed an electrical airplane. We said it's not the time. And what we always thought was the underlying problem driving this technology were the batteries. And so we always looked at the battery technology. And again, this morning, I spent about 4 hours looking at the battery technology. So I want to offer you a couple of perspectives that I've been able to find. So if you take a look at what's the most important thing as far as battery technology is something called specific energy. And it's basically watt hours per kilogram. And in aircraft and in flying vehicles, kilogram or weight is the most important factor. It's the driving force. So if you take a fuel or kerosene, Jet A, or just automotive fuel, we have about a specific energy of about 12,000 watt hours per kilogram, right? And if you take a look at lithium-ion batteries that are in your phone today, we have 265 watt hours per kilogram. And so what I found, and what's the most common battery on the market today is the lithium-ion. And that was always supposed to be the battery that was going to evolve and then go into these electrical vertical takeoff vehicles. And we always found that it was just not there. And specifically, again, reminding you, 265 versus 12,000. That's a huge difference. And weight is everything. So then the other battery that I found, which is kind of interesting, is up today this morning, was an aluminum air battery. So aluminum air battery has a 1,300 watt hours per kilogram. So it's about 9x better than lithium ion, but it's still lacking quite a bit as far as the kerosene-based fuels. Now there's the golden goose. And so the golden goose is actually the lithium air batteries. So lithium air is theoretical. It's not experimental. The theoretical limit is 11,140. It's just shying away from the fuel or kerosene-based fuels. So, but that doesn't exist on the market. It exists in the lab, but it's not actually being able to be taken out of the lab yet. So we have two underlying technologies. We have lithium-ion and aluminum air. And so as we talk through the panel today, it's really fascinating that I want to hear about the batteries that they're using. And hopefully, just to give you a kind of perspective, I took a look at two vehicles today. So first one is Robinson R-22 helicopter. So basically, I turned the helicopter electric. I gave credence as far as we're changing out the engine. We're putting in electrical motors, so we have a lower weight. I added 2 passengers, which is what the helicopter holds. And coming through the math, using lithium-ion batteries, we have a 13-minute flight time. Sorry, speaking so long. But,
It's okay. I'm just getting toward the edge of my chair here.
Oh, really good, interesting stuff. So lithium-ion batteries, 13 minutes flight time with a helicopter being electrified, if you will, electrified. So then looking at the regulations, because of safety and reliability, IFR regulations require that helicopters have a 30-minute flight time with reserves. So at 13 minutes using lithium-ion batteries, well, that doesn't even fit in the current landscape of regulations. Okay, well, let's try to do something else. Let's put aluminum air batteries in there. So aluminum air, given the 9x battery density, of 180-minute flight time. So that's 3 hours. Now that's interesting. So at that point, with IFR reserves of 30 minutes, we meet the FAA requirements. Cool. All right, so next. Sorry, guys, but this is, it's been 4 hours on this. Come on, I gotta do something with it. So a lot of the technology in the Uber paper and Joby, and as well as what I gathered from Airbus, you guys are pretty secretive, by the way. So I electrified an Icon A5. So the Icon was really interesting for me because it utilized the same technologies that a lot of the panelists talk about, which is specifically a safety parachute for flight termination and carbon fiber. Very cool. So Icon A5 went through the thing, electrified it, came to the conclusion, again, taking out the larger 912 Rotax engine, putting electrical motors in there, And so what I found is with lithium-ion batteries, we have a flight time of 18 minutes. Now, again, FAA requirements, just IFR is 45, VFR, visual flight rules is 30 minutes. So lithium-ion is no way. But it'll give you 18 minutes, but you can't legally certify it and carry people on them. So aluminum air, wonderful. So here we go, 88 minutes. So that's pretty much an hour and 30 minutes almost. Very cool. But so let's talk about aluminum air a little bit. So aluminum air
So
is...
Aleksey, can I ask that you allow someone to comment on some of the interesting points you've made?
Absolutely, just one last tidbit, and then it's all open for business. How about it? So I just did want to mention aluminum air. So there's a company in Israel that's working on it. They appear to have placed it into cars, but there's two fundamental problems with it. The first one is it has to be replaced, from what I gather, about 1,200 miles. What that means is you have to completely throw out the entire battery and put a new one in. And so what you're talking about when you do that is equivalent energy cost, even though you're putting electricity into that, by the time you replace the battery, is equivalency of gasoline. So you're actually not getting any more efficient as far as cost per kilowatt hour, like a Tesla, which is using lithium-ion batteries. It's less cost than gasoline. But even if you're using electrical technology with this aluminum air battery, you have electrical airplane, but it costs the same as gasoline. So that's kind of what I gathered this morning. After 4 hours of research.
Good.
How about it?
So after that design exercise, that was good. Any 30-second comments from the panelists?
I got one.
Good.
We're not electric.
Neither are we,
At least not our first product. Yeah. We use the Rotax in it.
Cool.
Yeah. But actually, we've looked at it a lot as well. We think that there is significant potential, particularly for the urban VTOL mission, primarily because one of the big factors, as was mentioned, is noise, right? And there are a lot of things that drive you towards things like distributed propulsion systems. And I don't think anybody's going to deny that battery technology is a huge limiter to the potential missions, and that the Part 91 regs, the minimum required reserves, are a huge barrier. That's one of the big regulatory barriers for achieving this type of urban VTOL mission. So I'm not going to argue that.
So, our aircraft is electric. So I agree absolutely that the batteries are a limiting factor. The IFR requirements in Part 91, I think we'll find are going to be more flexible as time goes on. For example, our aircraft currently has a range, including the reserve energy requirement, of something like 30 to 50 kilometers, depending on what we use. But if you include the loiter time for the reserve energy requirement, that adds something like 60 to 80 more kilometers of range, which shows that the reserve energy is a bit of an insane requirement to put on vehicles. I think once we work with regulators, we'll find that they'll be more willing to accept rational analysis when analyzing vehicles in an urban atmosphere.
So we actually talk about this in our paper as well, thinking about the excess reserve energy requirements for air taxis. Well, if you're flying a 50-mile flight at 200 miles an hour, that's 15 minutes of flight time, and the current excess reserve energy requirements are 20, 30 minutes. And so you don't actually need that much time. It's actually, as Zach said, pretty absurd. And so I think as we begin to work with the FAA and EASA, which have shown the tendency to accept consensus-based standards, that's certainly one area where we're hoping to make a difference as well, especially as we bring together not only vehicle manufacturers, but folks that are developing batteries, and also folks that are working on charging technology. We've talked to a number of companies that are thinking about not only how do you make batteries better, but how do you charge them more efficiently. And one other thing to keep in mind, and we also talk about this in our paper, is charging isn't the only answer. And so charging is absolutely something we want to do quickly, but different operators or different folks are thinking about, well, what if you do battery swaps? And you can kind of take your time charging these batteries, and so you really only need enough time to do your maximum mission length. And if that's 50 miles, great. If it's 100 miles, obviously you need more, but that can start to increase over time.
Very good. So I think a lot of us are very excited about the potential for batteries to exceed 400 watt hours per kilogram. We'll see whether it's the regulatory things that help or the technology that helps, but there are lots of other things. I thought I would actually in the spirit of difficult questions and in the spirit of trying to involve the audience a bit more, I would ask another very difficult question that doesn't involve any watt-hours per kilogram. Given the lack of, parentheses, especially gender, on this panel, this diversity on this panel, and the general dearth of diversity in the tech industry and in the aviation community, what steps are being taken, or are companies taking, in order to ensure that these technologies are marketable and accessible to diverse communities and designed with all in mind? I should say that Silicon Valley's problem with at least age diversity, I represent a little bit of that, but I agree that it's not a very diverse panel. But that being said, we certainly tried very hard in Silicon Valley to hire a more diverse workforce. It's actually pretty difficult. Thought I'd ask Zach how Airbus has done.
I agree it's been difficult. I think that it's important that we encourage women in engineering. I think one of the key ways that we have of looking for diversity is targeting organizations like SWE, Society of Women Engineers, to see if they have people that are interested in positions here. Airbus is an international company, so in terms of beyond just male, female, we have products all around the world, and it's very important for us to target all different cultures, and I think that's something that's very important as we continue to design aircraft. So,
anyone else on the panel want to speak to that?
Go ahead. So, is my wife in the audience? There she is. Anna co-founded Terrafugia with me. She also was an MIT undergrad and grad student. We met at MIT in grad school. And Terrafugia has about, I was just doing the numbers in my head, we're about 20% female. So I think we're, there's a long way to go, obviously, but as diversity goes, I think we're doing all right. So far, so good, at least. I'll probably get crap from that comment later.
Yeah. No. Nikhil.
Yeah, so I think Dr. Kroo, you bring up a great point, and at Uber, this is something we think about a lot because, as I said earlier, our mission is transportation as reliable as running water for everyone, everywhere. So prior to Elevate, I was a product manager for the rider experience team, and for the last year, I've been working on the new Uber app, which came out last week. And as part of that, one of the core things that I pushed our team to do was focus on rider research. So along with my team of about 6 designers and my manager, who's kind of head product manager for the entire project, we flew all over the world. We flew to China because we operated there at the time. We flew to India. We flew to Europe. We flew to many different cities in the United States, really relentlessly testing every single piece of the rider experience. And we tried as hard as possible for that, for those riders that we included in those studies to be representative of our user base. Because if you look at markets such as New York, where getting a taxi cab, especially in the outer boroughs, especially if you're a minority, is difficult to do, but Uber intends to serve every customer. And so absolutely, when we have a VTOL offering, we will absolutely take the same exact steps for customer obsession, thinking about how can we optimize every single part of that journey and how can we make it applicable to not only all types of riders, but riders all around the world.
Okay. Jeff, were you going to say something else?
Sure. So we think about one of our goals of our fund is to increase mobility. And so this is trying to get costs down on a per mile basis. And so this will apply, and as we get to that goal, be able to be applicable to everyone. From an investor standpoint, it's a little tricky. Hanging out with other middle-aged white males, we are going to have a particular network that often looks like us. And so this is something where the solution is relatively right there, which is break out of that network and be able to make sure that you're incredibly open to be able to have different styles of communication. We've had a couple of pitches that, from a pattern matching standpoint, was different than what we had been used to from a style, from a whether that's an aggressiveness level or whether that is the types of questions or how they field or how people interact. And so this is simply just an understanding, I wouldn't say tolerance, but it's an acceptability and communication type of answer, being able to break out of that network, break out of that mold. That's something that we've been very focused on.
Okay, good.
I guess I should say something too, right?
No, you don't have to. You've had your time.
Yeah.
Just teasing you. Thanks. Aleksey,
No, it's
seriously.
okay.
Okay. Here's a broader question. What is the most important innovation in transportation, or you could think about this more generally, during the last year?
I would say transportation generally doesn't change on a time scale of 1 year. If you look at the history of transportation changes, they tend to happen over the course of about a generation, which is actually one of the biggest challenges in getting capital for this type of venture. So I'm not sure I can answer that question. I think that our whole approach is that this type of magnitude of change that we're talking about is probably a generational type change. We need to break it down into smaller chunks that are investable. This kind of counter the 0 to 1 whole philosophy of some people in Silicon Valley. But I think that because it is a societal change, that societal changes really tend to be that type of generational timescale.
Certainly, but I think that many people would probably agree that it's a surprise at how quickly electric cars have been accepted at least in California, but actually much more broadly. And I think that some of the motivation for technical innovation is going to be spurred by a whole bunch of things that operate on electric power, and we shall see what that is. Jeff?
I think what Tesla's doing with over-the-air updates is incredible. This is something that we all have supercomputers in our pockets, and we have over-the-air updates almost too often. But the concept of here are cars that we own that get better over time, that this is something, it's a radically different shift. I wouldn't call it necessarily a technology. This technology has been around for a long time. But when you think about the business model of having cars and transportation and vehicles that are actually improving over time because we're actually updating them with software, I think it's huge.
Okay.
So I moved here about 4.5, 5 years ago, and one of the stark differences I noticed was from then to today is that now I can drive around Mountain View and see little driverless cars. The first time I saw it was a guy sitting in the car eating a piece of fried chicken, just getting tooted around. And to me, that was amazing. And that happened in just the last 5 years. We also see huge interest in things like Hyperloop. There's basically a much larger interest in different types of transportation, from autonomous cars to electric cars, and even the work that the various vertical takeoff companies are doing around here.
Right.
Sure. Yeah, just one last one to offer up. So Supersonics, it's been just finally this year, I think, was the huge breakthrough. There's been a lot of attention on Supersonics. We have companies like Boom going after it. We have Spike. We have Aero, which I'm sure you'll know quite a bit about. And then, of course, Gulfstream is working on that as well. And so there was a breakthrough technology where it's basically distributing the sonic boom over the nose and allowing basically supersonic airplanes to fly supersonic over continental United States, which is a huge breakthrough. And so Gulfstream is working on that. I'm pretty excited about that. So we'll see how they end up with that.
Yeah, real quick, and for me, it's been thinking about how society has changed its views on personal car ownership. Uber actually recently did a survey, and we found that 10% of millennials had actually given up their car or decided to forego purchasing a car because they use Uber. And so that personally was super exciting to me, not because of the Uber angle, but thinking about all the effects that has on society and our community, and what can be done by the space that's hopefully not taken up by those cars, and thinking about the effect not only here in San Francisco, but all around the world. Even my own grandparents take ride-sharing services in India, And that's super exciting to see in a place that does have more congestion than we have here, more pollution than we have here. And I think that's a trend that's only going to further continue to accelerate.
I guess this one might be for Zach. There's a very strong focus on vertical takeoff and landing. What are its advantages?
I think it enables, that for me, it's the point-to-point transportation aspect. You don't need a runway, and I think that is a huge enabler in terms of the number of places you can operate out of.
Okay. It does mean that if you don't have an area around an airport, you may be operating closer to other people, and then the noise issue becomes problematic in two ways. One is that you're closer to people, and the second is that you're operating a vertical takeoff system, which requires a lot of thrust.
Yes, of course. That noise is one of our top concerns, and I think it's going to be one of the most difficult factors for any of these VTOL projects to get past in the upcoming years. I think that if you look at around the world, for example, the Sao Paulo Ubercopter project, you're already seeing the deployment of helicopters, which are arguably substantially more noisy than some of these other vehicles, including ours. So I think there shows that project has shown an interest in this space, despite the fact that they're more noisy.
So there are lots of numbers kicked around for how noisy a vertical takeoff airplane has to be. I do think that I agree with you that noise is going to be one of the most challenging pieces of this whole thing. Do you agree with Nikhil's 67 dB at 250 feet, or was that it?
It's half of as loud as a medium-sized delivery truck. So I think we said a medium-sized delivery truck's between 65 and 70 dB. And so thinking about how can we be half as loud as that, and more importantly, how do we just blend into the overall noise in the community?
Mm-hmm. So I think that's an excellent target number. Firstly, the beautiful thing about vehicles that have a hybrid lift, in other words, they have a vertical lift system and wings, is that when you go into forward flight, the noise drops tremendously, and you can easily hit these numbers. So it doesn't solve the vertical takeoff and landing portion, but you're talking about seconds of time where it's at that decibel level.
Right, and hopefully those seconds are not in your neighbor's backyard, but
or
at some place like Nikhil showed where there's some infrastructure there. Yeah. Okay, another difficult question here. How will you solve the problem when an airplane like this hits a house or a kid in the street? How will code be written in those circumstances, and code you might take as regulations in this case? Do you want to say anything about accidents, and will this be a problem when the sky is black with little airplanes? Or
I hope it's not black with little airplanes, firstly. When we're deploying these vehicles in large numbers, hitting the safety targets of 1 in a billion or even better is going to be a critical factor in any of these things. And certainly, an airplane will crash eventually. Airplanes do crash, and taking whatever the results of that accident were in the investigation of that, and maybe pushing these over-the-air updates to the vehicle, the autonomous systems are on board, is going to be a critical aspect of it. I think that the FAA has talked about some of these higher risk certification categories recently, but when you're talking about getting thousands of vehicles out there, I think there's no choice but to have safety targets that are much, much higher than we expect in automotive and aerospace in general.
I think they have to be more aggressive than driving, right? Because today people know that commercial aviation is in general safer than driving, and driving is only going to continue to get safer over time. You see autonomous ground car technology and its promises of improving automobile fatalities. So I think from the onset we've got to think about how can flying be twice as safe as driving, and I think only if we set out ambitious targets like that can we actually hit something that is not only going to be safe but is also perceived as something that's a safe way to travel. Because as Zach said, incidents will occur, but we need to, at the onset, be prepared for those and make sure that they happen as infrequently as possible.
I'd also add to that I think that because these vehicles are entering to a space that exists today, that the public demand for aircraft safety is much, much higher than that for vehicles. That if you had thousands of aircraft crashing per day, which cars do regularly, that would be completely unacceptable to the public, despite the fact that they're safer by far than cars. So this is again why I think that targeting these much higher safety levels is something that not only that we have to do as engineers and developers, but it's something that the public will demand from us.
Dietrich, you're probably closer to fielding some commercial products than many people here. What do you think about this concern?
Well, I think it's a critical concern. Our strategy is really to push forward and implement a number of safety technologies that are actually not even required. And a number of the most mature pieces of the autonomy software that we're looking at are things that have been developed over 30 years and have field experience already that we're talking about implementing on our existing hardware. So it really is one of the largest costs for vehicle manufacturers, general aviation aircraft manufacturers, is products liability insurance. The fatal accident rate today in general aviation is nowhere near as close as low as driving. It's better than riding a motorcycle, but it's not as good as driving. So we have a lot of room for improvement, and there's a lot of low-hanging fruit, frankly. There's, the leading cause of accidents, fatal accidents in general aviation, is simply loss of control. The next largest is controlled flight into terrain. I mean, some basic autonomy, full envelope protection, addressing loss of control issues, ground collision avoidance, automatic ground collision avoidance, addressing controlled flight into terrain. You take care of those two leading causes of fatal accidents, and you're almost reducing the fatal accident rate of general aviation by an order of magnitude. So there's huge low-hanging fruit to be had in the safety world with autonomy.
So we have been talking about a range of possibilities for future air transport. Jeff, I wondered if I could ask you what you see in this diverse set of possibilities might be the business opportunities for people to support this kind of thing in the future.
Sure. From an investor standpoint, we've shied away from some of the hardware in this space. The enormous amount of regulations, plus actually building and in low volume, is really tricky and requires an enormous amount of capital. And we think that there are a dozen or so players that are kind of moving in this space. We're actually particularly interested in the software players that are in this space. And so Carl mentioned earlier the challenges to getting code actually certified. And so we think a lot about that. The autonomy in the air is easier than autonomy on land, but there's still quite some challenges there. And the redundancy that's required is incredibly important and we think that there's a significant amount that could happen on collision avoidance and from a software standpoint.
Okay, thank you. Someone from the audience asks, could the skies get overcrowded? And I was asking facetiously about the skies black with these vehicles, but 101 is probably black with cars, but when you go from a one-dimensional distribution of all of these cars to a three-dimensional distribution, you can do the math later, but it's surprising how much space there is. But it still means that we have to do an interesting job of air traffic control. Anyone want to say anything about
Sure.
that?
So again,
Yeah,
sorry, the pessimist here, but I mean, if we look at the futuristic scenarios, I don't know. There's a bunch of movies, but you see like these highways, right, of flying cars, but they're still in a traffic jam, right? And so as I think about the regulatory environment here in, let's say, the Bay Area as an example, where we have 3 major airports. And if you take a look at an air navigation map, it's really complicated. And so I think the FAA's stance, again, for safety and regulatory environment is to paint these sort of highways, where helicopters can travel and whatnot. And so it becomes less three-dimensional and more constrained than you guys think. And so then we think about these cars, let's say we darken the sky with them, which is always a fun line in aviation, is so what you do imagine is going to be less separation, and I do kind of foresee that there may be some kind of traffic jams, especially with SFO being as busy as it is. You can't just start letting airplanes on 3 different kind of tracks to go through SFO space, and it's cutting straight through the middle between San Francisco and San Jose. So that's just kind of my perspective. I think it'll be more challenging than most people think.
Yeah, so look, you are seeing some of these air corridors emerge, right? Governor Cuomo earlier last week announced a stretch of an air corridor between Syracuse and Rome, New York, where experimental aviation could take place. And so absolutely kind of see your point there. I think one thing that's important to push on is ride sharing and thinking about this is not why, at least in my mind, I don't think folks are going to own these vehicles necessarily and operate them on their own and have them sitting around or operate them in 1 or 2 person aircraft. I think that's why we talk so much about 4-person aircrafts and thinking about, well, how can we combine folks that are going from the same point A to the same point B and put them in the same aircraft and get utilization as high as possible. And we've seen with Uberpool here on the ground, I think 20% of riders globally in Uberpool cities choose to take pool. And that number only continues to go up. And so thinking about, well, what does that look like in the air and how do we make sure that riders going from A to B are combined within the same aircraft, so we do lower the number of actual vehicles in the air, and it's not just all of these individual, I think you showed one of those single-person pods. That's the last thing we want, because then obviously the CapEx per person and the passenger cost per mile is a lot higher. And not only that, but then you start to darken the skies. And so my vision is absolutely to put as many people into one vehicle as we can and optimize around that.
So I'll chime in a little bit on this. Particularly with respect to airspace, we get this question all the time. And really the constraint on the potential market, the potential capacity of any sort of system is really, so how many vertiports do you have, or vertistops, or whatever you want to call them? How many do you have, and what's the throughput of each one in terms of the people per vehicle and the vehicles per hour? How much can you, and if you run the numbers with realistic assessments for, one vehicle in sort of the 500-foot corridor that's going to take you up and down through, over that vertiport, you do want to have more people per vehicle, and you want to spend as little time as possible stopped on the ground.
Yep.
And you want to get in and out of there real fast. And if you can't do that, because you're probably realistically talking about maybe a few hundred vertistops per major metropolitan area, at least in the foreseeable future, maybe things will all change 50 years from now. But in order to have a measurable impact on traffic congestion, you really have to drive towards that, optimizing how fast you get those things in and out.
Yep.
And that's the only place where you really have congestion issues, is right near, because that's the neck of the system. That's the bottleneck to everything.
Yep. Yeah. You definitely bottleneck on operations, and I think that's one area we'll absolutely have to focus in thinking about, well, how can, in our paper we talk, we're a lot more conservative, but we've been doing a lot of thinking around, well, how can you get that loading and unloading time as low as possible? Can you get it to 30 seconds? And I think when you have things like autonomy, when you really focus on the pilot experience and the operations of the vertiports, I think you can. And I think that's something that's going to continually improve.
So let me ask a question from the audience here that deals a little bit more at the regulatory side of things. A key part of solving these problems seems to be community local government buy-in. This group feels exclusionary of these factions, which I should apologize for, but I don't think this group is unaware of those factions, and it's an extremely important part of being able to operate any of these vehicles from delivery drones to flying cars. The question is, how do you see the relationship with local regulators, as opposed to the FAA, having an effect on this field? Who wants to start out with that? Anybody?
I can start. I think that the customer is these local people. When Uber writes their paper about who they're servicing, it's those people. So those are the people that the opinions that are going to matter the most in these things. And we brought up noise before as one of the critical requirements. And 3 million Santa Cruz people that are complaining about noise of the rerouted air traffic over the Santa Cruz Mountains. And that's clearly something that's going to be very valuable to talk to communities, develop these systems that perhaps barrier noise, shield them from noise. I think that the possibility of moving people farther, faster, for less money might kind of change their point of view. If you can go to Napa in 30, 40 minutes, and you can do that for tens of dollars, it might allow people to kind of expand their viewpoint of what's possible when these vehicles enter this space.
Yeah, I think community acceptance is going to be key, and it's going to be difficult. Noise is a huge part of that. Safety is another huge part of that. When you think about helipads, and I showed kind of there are 28 emergency landing sites, but there's actually only one helipad in San Francisco, and that's because of noise. It's because when you want to get a helipad approved for operations, you have to go to the city, the county, and the state level, and often it gets blocked at the city because every time you even propose using one of these landing sites for aircraft, even for medical purposes, the entire community gets upset, and people freak out about the noise, and people get upset about it, and understandably so. And so this is an area where Uber has experience and has the relationships with cities, and we've already begun this outreach with a number of cities worldwide that are actually quite excited about the technology and excited about all of the different manufacturers in the space and where the technology is headed. And so this is one of the concerns that's brought up a lot is noise and how will we interact with ground transportation and public transit in the community. But it's something we're aware of, and I think all of the vehicle manufacturers we talk to are well aware of. And so it's something we're excited to take on head on, and I don't think it's something we should necessarily thwart or avoid, but it's something we should attack and figure out how to make it not only provide the time value proposition, but also make sure we're not worsening any of the conditions in terms of noise or safety or congestion.
So I think it's certainly our responsibility to think about this. I think it's our responsibility to the local communities and the community more broadly, but it's also our responsibility to this burgeoning industry. So if all we do is show that we can take off and land with 105 dB at some distance, and we annoy everyone before anyone really starts to be producing these things, we'll have a very much harder time dealing with local communities and local regulatory authorities who will be all set to say, no, we don't want this here. So it's really very important, if we want to see some of these things happen, to be able to act very responsibly, not just in the noise field, but in safety and everything else. Okay, so we have about 8 minutes left, and let me pick something here. Someone notices that Zach is building a one-person airplane, and the Uber paper says 4 people, and Nikhil says maybe more than that. Why do you decide on all these different numbers, and shouldn't we all agree?
So I can tell you how we got to our numbers. When you look at what's the most compact, smallest vehicle you can build, the obvious answer is a single passenger vehicle. And it does open up a lot of possibilities for what you can do with that vehicle if it is single passenger, including doing things like using high rate manufacturing techniques. And you could probably extend that to 2 passenger vehicles, but when you're in the 4-ish passenger range, stamping out carbon fiber or metal parts becomes prohibitive. There's not very much tech that exists today that can do anything like that. So in terms of optimizing direct operating costs for a vehicle, you'll find that when you account for manufacturing and those kind of things, that the 1 or 2 passenger range enables cheap production, cheap manufacturing, and also allows for batteries to be more useful. As we found that as you get to bigger and bigger vehicles, the battery occupies a larger portion of the aircraft. So I think the smallest viable product is a single passenger vehicle for those exact reasons.
Yeah, so to be clear, I don't think we want more than 4. Once you get past 4, then it's difficult to utilize that aircraft fully. In our paper, we do talk about both 2 and 4, and we mainly talk about 4 primarily for ride pooling, as we talked about before, because it's super important to Uber that this isn't just for the rich people. It's not just for the 1% going out from Manhattan to the Hamptons or to Napa. Those are interesting use cases, but the commute use case is the one that's our hero use case, the one that we want people to be able to take take this every day on, and for that it's got to be cheap, and for it to be cheap you have to be able to ride pool. And you can't do that with two. I mean, you could if you've got two individuals, but you can't do that as cheaply as you can with four. If you have four parties in one aircraft, and during commute times, we've identified a number of these commute corridors, San Francisco to San Jose being one, or the Marina to even the Mission for a shorter distance, or a number of others, say in the LA area or the New York area. If you can do that, you can get it a lot cheaper. Understand that manufacturing is a concern, but aircraft have never been mass manufactured since World War II. And so I don't think we have a really good sense of, understood it'll be difficult and there will be a number of barriers, but we certainly think, based on the experts we've spoken to at NASA and a number of other manufacturers, thinking about, one day can we get to the mass production of four-place vehicles? I think we can, and I think it's ambitious but certainly achievable. And if we can, then that's what's going to allow this to be for the masses.
Okay.
I might go against you on that one a little bit. So 75 or 70 to 80% of commuters are single passenger. We have carpool lanes. I drove in here today, and the carpool lane was empty. There was packed traffic all the way here, and there's maybe less than 10% of people in that lane out in terms of occupation. So I think in terms of who are we serving? If we're serving commuters, then you're again back down to the 1 or 2 passenger vehicle. People don't carpool, and when you're talking about commuting, people want to go directly to their work. They don't have to stop off at 5 other places before they get there.
Absolutely agreed. I think it's disappointing and sad that the carpool lane was empty, right? And as you saw earlier, a lot of folks didn't take Uber here because Uber doesn't serve the commute use case super well. It is very expensive even to take an Uber pool from San Francisco down to Menlo Park or to San Jose. But if we make it simple, and if there's a limited number of vertistops in conjunction with ground transportation, so let's say you're going from A to B, and an autonomous car or just an Uber X picks you up at your home, takes you to a vertistop where 2 other passengers, you've coalesced the pickup and drop off, go get in that Uber pool VTOL, go to the other vertistop, you get in an AV, you get to your work. Then we can make it convenient for you. And we're already doing this. We do this in New York City. So when you take an Uber pool in New York City, if you're on a one-way street or if you're on a smaller avenue, we say, hey, why don't you walk 2 minutes to Broadway or to a larger thoroughfare, walk just a couple of minutes, go meet other passengers for a coalesced pickup or drop off, get in the Uber pool, and then same on the other end. And customers are starting to really understand why we do this, and when we do this, we can bring the price way down. And so it's an experience that we're already building into the app today, and you can imagine if we were to do that, but your time to your destination was 4 or 5 or 6 times faster, people would only be more keen to do so.
So Nikhil, let me mention that there are also some technical, not just social issues in getting bigger. These vehicles are just barely possible, or some would say just barely impossible right now. And so there's this multiplicative factor that the weight of the vehicle grows tremendously as you increase the payload, and then it becomes harder to satisfy noise constraints, et cetera. So I'm sure you will work with partners and evaluate that, et cetera. But I do think that the scalability is not infinite, or not even maybe to 4 or 6. So we'll have to see.
Yep.
I wanted to ask 2 more quick questions. One for Jeff. As Carl mentioned, the adoption is more of a generational shift. How does the VC community look at these startups and their solutions? Is there a palatable ROI?
I've talked to other investors. When we went to raise the fund, isn't autonomous vehicles, and we're talking terrestrial at the moment, isn't this 20, 30 years away? My partner and I said, no, this is 2 or 3 years away. And everyone said, no, it's 20 or 30. And then once Kroo's happened, it was like, oh, well, isn't everyone doing this? It was like already like a done deal, like everyone thought it was baked. We still run into this from a generational standpoint, though, of there's just clearly investors that do not see this, do not believe it, and just cannot understand that a robot will be driving their car. We see this great enthusiasm through universities. My partner and I both teach at Stanford. I have a lot of connections back at the University of Michigan. And so there's, we see this in the students. We see this in their excitement to disrupt the $5 trillion industry that is transportation. And so there is a disbelief at kind of the older end of the spectrum and an enormous amount of enthusiasm. Probably Elon Musk didn't have, probably had something to do with it, of just, hey, we can invent, we can build, and we can get funded, and we could potentially be acquired or have an IPO in this space.
Okay, so for the last question, let me ask Aleksey and Carl to talk just a little bit about this. The question was, what are the weather wind constraints of some of these designs? And you've both mentioned things about your designs that avoid some of the issues that some of us looking at lightweight vertical takeoff airplanes have. You want to say something about that?
So sure. So I think the Uber paper kind of mentioned it's really important to note that I think the beginning is VFR, which is visual flight rules. So there's weather constraints. And when I read the Uber paper, I think one of the first things that jumped to mind is San Francisco. And so, as we all know, San Francisco weather and fog coming in and out is difficult. So that's one of the first hurdles with these types of vehicles. I think the wind is less of an issue. I think there was also a discussion on lightning and ice. And I think most general aviation vehicles, if they're VFR constrained, don't need to have icing requirements. So I think that kind of goes through that. And then lightning concerns are general guidelines for building airplanes, so I think that's taken care of. But I think what's really important to realize is as these vehicles kind of, if they do exist, start coming alive, is it'll be first VFR and it'll be really weather limited, which is important. And then as the pilot gets trained, because we have 4 people, 1 pilot, because it's not full autonomy, right? Because it's the easiest way to certify these vehicles. So we have a trained pilot, then they become instrument rated, and so then you can go through the weather. But that'll be kind of the cascading effect to kind of create a more day-to-day platform for that. So again, weather VFR certification to the pilot is really important. I kind of am interested, I think I understand the 4-place perspective as far as what you guys mentioned, but I just want to quickly touch up on it. So the pilot is the more expensive piece of the whole entire puzzle, right? So as you grow the vehicle, I understand that occupancy rates go up and down, but there's only 1 pilot and there's more people. So it's kind of interesting. You guys, Uber has the data, without a doubt. But you can guys kind of put the pieces together. But that's kind of my take on it.
Great. Carl, do you want to say anything about that?
Yeah, I mean, weather is a huge issue for any sort of light aircraft. There are ways of addressing it through vehicle design, through higher disk loading, through higher wing loading. In terms of, ride quality is a big issue. I mean, for our vehicle, it's a light sport aircraft. It has relatively light wing loading because there are requirements on stall speed. And that's one of the barriers to entry. Is there are a lot of people who simply don't like flying in little airplanes because you do get bounced around a whole lot more than you do when you're driving a car. For some of the other concepts that are being developed here, with higher disk loading, with higher wing loading, those sorts of issues can be addressed. From a weather sensitivity perspective, in the long run, you've got to be able to operate in weather. In order to have a truly scalable, robust system, you've got to be able to fly in what today is IMC, and one of the big regulatory barriers to doing that, of course, is that if you're going to fly in IMC today, you've got to fly under instrument flight rules. And to fly in instrument flight rules, you've got to be in voice communication with air traffic control. And right now, ATC is not at all set up to abandon that system and go to a nice digital system that would simply exchange information. So that's another huge challenge that we're going to have to overcome in the long run to make a system that's truly robust and scalable.
So I think we've touched on a number of things, and I can take a hint. So I'd like to say thank you to our panel for some very thoughtful responses.